when you see me go out of the room, if you'll just say testing, talking like you're normally going to.
Okay.
All right, testing, making sure the audio works. Could everyone hear me okay? Great. We're going to find out from Amanda whether they can hear me out there.
Okay, I think we'll go ahead and get started. Can everyone hear me okay? All right. Thank you so much for being here with us on this apparently chilly night. I don't know about you, but I wish I had brought a jacket. But it is potentially clear outside, so we're still not 100% sure. But those of you who have been with us before, you know we've been cursed for all of 2026 with clouds. And so this might be the night that we break it. We have our weather team on the roof, and they'll be sending me updates throughout the night. But no matter what, we have a wonderful talk in store for you all tonight. With a show of hands, can you let me know if this is your first time here? Ooh, all right, we've got lots of new people. My name is Amanda. I'm a lecturer here at the astronomy department. I'm also the outreach coordinator, so I get to host these talks. We always start with announcements, so to let you know what the night will look like, we will begin with trivia. Then I'll tell you about our fall programming. We'll have our fantastic speaker. We'll do Q&A, and then there's a big question mark around observing. Hopefully the skies will stay clearer, but we don't control the weather, so no guarantees. All right, so we'll start with trivia. The way this works is that I'm going to show you one question at a time. There are 5 questions total. You'll have time to think about it. Collaboration is strongly encouraged. Talk to people around you, even if you don't know them. That's when you learn the most. And then after I think you all have discussed enough, I'll say 3, 2, 1, vote. At the same time, everyone will show me 1 if you think the answer is A, 2 for B, 3 for C, 4 for D, and 5 if we have an E. Make sense? Okay. question 1. So Rebecca is going to explain what cosmic rays are throughout her talk, but I'll just give you a little teaser that they're energetic particles. And they are flying towards you right now. So let's think about how many cosmic rays hit Earth's upper atmosphere every single second. No worries. Okay. It's always great when I have to rudely cut off conversation because that means you're having deep discussions. But let's see your thoughts. 3, 2, 1, vote. All right, I see lots of 5s. I see some 4s. I see a 3. Do I see a 2? I see maybe a 2. I don't think I see a 1 though. All right, the answer is 1,000,000. And so that's just in 1 second. There are many seconds in a day. There are many, many seconds in your lifetime. So that is a lot of cosmic rays that our body could experience. I told you all cosmic rays are charged or highly energetic particles. So it might sound scary that you experience so many of them. And so our next question is, what protects you from getting hit by these cosmic rays? Okay, I'm going to bring us back and count down to our vote. 3, 2, 1, vote. All right, I see 1s. I see 2s. Do I see a 3 or a 4 or 5? I don't think so. 1s or 2s, so something about the Earth, and it is the magnetic sphere. If we didn't have that magnetic sphere, our bodies probably would have evolved very differently, or life might not have been possible on this planet if it didn't have protection from all of those energetic particles. All right, so we've talked about these energetic particles, but the big thesis of the talk will be, where do they come from? Why are they here? How do we learn about them? And so we think they must come from something really energetic. So one of the things that are really energetic in the universe are astrophysical jets. So they occur when material is being expelled from astronomical objects at high energies. How long are the longest jets? Okay, I hear conversation dying a little bit, so let's vote. 3, 2, 1, vote. All right, I see 4s, I see 5s, I see 2s. Do I see a 1? No, I don't see a 1. All right, so no one thinks it's the distance to the moon, and that is correct. In fact, it's the length of a galaxy cluster. So this jet is probably at the center of a galaxy. It extends far beyond its own galaxy and the length of a whole giant group of galaxies. So this is incredibly, incredibly powerful. All right, we'll now examine another source of lots of energy in our universe, a supernova. This is an X-ray image of the supernova remnant Cassiopeia. A, how hot is its gas shell? So these colors that you're seeing, that's its gas shell. Okay, let's vote. 3, 2, 1, vote. I see 1s, 2s, 3s, 4s, 5s. That's what I was expecting. And so this is why astronomers, we all should use the same units. This is comparing apples to oranges. Very tricky to do, but it is in fact A. Okay, we have one more question. So you all now know that 1 million or millions of cosmic rays hit our Earth every second. So maybe not all of them are interesting, but some of them catch the attention. And so what do scientists call the most energetic cosmic ray ever observed? Okay, let's vote one last time. 3, 2, 1, vote. I see 4s, I see 3s, I see 2s, I see a 1, and it is the oh my god particle. Probably because someone saw it and went, oh my god. And scientists are not always good at naming things. All right, a round of applause to you all for playing. Okay, so our announcements, we already have our fall lineup. The dates are TBD because we have to wait until after classes start to book this room. But our first talk is going to be on dark matter. Then we'll have a talk on the intersection of art and astronomy. Then one on galaxies. And then we're going to have a 100th birthday celebration for our dome because it will be turning 100, and that will focus on the history of astronomy and the work that's been done on our roof. So being on our website and our mailing list is the best way to get the announcements for all of these talks. But until then, we have a fantastic talk tonight. I'm going to hand it over to Rebecca Deasing.
All right, thank you so much for joining me here tonight. Again, my name is Rebecca Deasing, and today I'm going to talk a little bit about cosmic fireworks and what we can learn from their shrapnel. And so I want to start by drawing your attention to this particular cosmic firework. You might recognize it from some of the earlier slides where we were doing trivia. This is Cassiopeia A, that same supernova remnant we looked at before. So this is what is left over after a star explodes, in this case some 300 odd years ago. The difference is that this image was actually taken with the James Webb Space Telescope. So this is an infrared image, and the colors that you're seeing there, the kind of yellows and reds and pinks, those are all different elements being excited by the explosion. And so those can actually tell us what exploded, what material was the star made of before it blew up. And then that white fluff that you see around, that is what we call synchrotron radiation. This is radiation light that is produced when the explosion accelerates electrons to very near the speed of light. Those electrons become cosmic rays, as we talked about. And those cosmic rays, those electrons, go on to interact with magnetic fields. And when they get deflected by the magnetic field, they produce light as well. And so when we're looking at that white fluff, we are really looking not at shrapnel, but at shrapnel of shrapnel. We are looking at the byproduct of the electrons that were accelerated by an explosion. And so this is actually a very indirect probe of what's going on, of what this explosion is doing. And so a lot of my work is focused on trying to figure out how we can bridge that gap, how we can go from the light that we see to the underlying explosion that made it. But before I go into that, I also want to take a step back and set the stage for what we call transient or time domain astronomy as a whole, and start by reminding everyone that for most of human history, we thought the universe was a very static place. So if you go to somewhere with a dark night sky, maybe not New York City, but this was taken over Lake Placid, and you look up and you see the plane of the Milky Way and all of these stars, you're going to see almost exactly the same stars, the same plane of the Milky Way that you would have seen hundreds of years ago, that indigenous people would have seen thousands of years ago. And so in most of human history, we assumed this is how it is. You know, we know that the planets move, but pretty much everything is static. Pretty much everything is infinite and constant. And yet, we had our first evidence a few thousand years ago that that's not the case. So the first record of some sort of not so static universe was recorded by Chinese astronomers in the year 185, when they wrote of a guest star, a new star that appeared in the sky. It displayed colors that were both pleasing and otherwise. And then after about 6 months, it disappeared. And so there was something that showed up, something new that was there, and then it wasn't. And then if there were a number of these actually recorded by Chinese astronomers, roughly every 100 years or so. But in the Western world, the first record of such an event was written down by Tycho Brahe, a relatively famous astronomer. And back in the 1500s, 1572 to be exact, he published this work, De Nova Stella, of the new star, or on the new star. This is actually where we get the term nova from. It just means new. And he showed that, there was this new star that appeared in the sky. He gave us this nice little map to look at. And if you know your constellations, or you read the Latin underneath, you'll see that this is in the constellation Cassiopeia. And if you point a telescope at that spot there today, specifically an X-ray telescope, you see something that looks like this. This is Tycho's supernova remnant. And so, if we fast forward to modern era, we don't just get these supernova remnants in our galaxy, but we also see that the sky is full of these fireworks, particularly if you have a powerful enough telescope to see them go off in galaxies that are external to our own. So in our own galaxy, we get about 1 supernova every century, but if you can look at all, or at least a sizable fraction of the galaxies in the universe, then you see all sorts of different supernovae going off. So this is a graphic that was put together by the Zwicky Transient Facility. This is basically a telescope that maps the sky over and over and over again, looking for changes. And every time it records a change, every time it sees a firework, it makes a little dot. And so those little blips are all different cosmic fireworks, mostly supernovae, exploding in our sky. And you can see that over the past decade or so, the Zwicky Transient Facility has recorded over 10,000 of these. And actually with next generation telescopes, so the Vera Rubin telescope, which is coming online now, we are expecting to have millions of these objects in the next decade. So we know that the universe is full of fireworks. What are they? Well, there are all sorts of fireworks, all sorts of explosions and outflows and collisions that I'm interested in. But the most common, and the one that I'll start with, is supernovae and the remnants that they leave behind. And when I talk about supernovae, there are kind of 2 physical categories. You'll hear a lot of classifications of supernovae, type 2, type 2n, type 2p. But all of those are mostly just classifications based on their spectra, based on what they look like. The main physical categories are these core collapse supernovae and type 1a. That's a holdover from that spectral classification that I was talking about before. So if you start with a core collapse supernovae happen when you have a very massive star. It needs to be about at least 8 times the mass of our sun. And if you have that very massive star, what's special about it is it doesn't just burn hydrogen into helium. It doesn't just fuse hydrogen into helium to support it against gravity. It can actually burn helium into carbon, carbon into neon, and on until it actually fuses silicon into iron. What's special about burning silicon into iron? If you are massive enough that you have a hot enough core that you can burn silicon into iron, you can reach the end of the road for nuclear fusion. If you try to fuse iron into a heavier element, put 2 irons together, you actually lose energy in this process. That's why we fission heavier elements like uranium, but fuse light elements like hydrogen. And so what happens is you have this iron core, and the star is trying to fuse it. It's trying to push these iron atoms together to make energy, but it's just losing energy. And so it loses all of its support against gravity, and the core collapses. And so now you have a little nugget left over. This is what we call a neutron star that is extremely dense, extremely hard, and all of the outer layers are going to fall down on top of it. And so if all the layers fall down on top of it, they're going to hit that neutron star that formed at the center. They're going to ricochet off, and you're going to get an explosion. And so this is what we call a core collapse supernova. It is the rebound of all of those outer layers hitting that core, that neutron star that you just formed. The other option is what we call a type 1a. So a type 1a can actually start with a more ordinary star, or a more ordinary dead star, I should say. So a type 1a starts with a white dwarf. A white dwarf is what our sun is going to become when it dies. So a white dwarf is the exposed core of a dead star after all of the outer layers have kind of been blown off. It's no longer doing nuclear fusion. You've just got a nugget of either helium or sometimes carbon and oxygen just sort of sitting there slowly cooling down. Pretty boring. But what if you put that nugget in a binary? What if that white dwarf has a companion that's orbiting around it? Well, if you have 2, sometimes if there is any mass transfer between the 2, so one is eating material from the other, you can actually make that binary smaller or tighter. You can bring the 2 closer together. And if they get too close, they can actually merge. Now, if you merge 2 white dwarfs, you can do a lot of crazy stuff. In particular, white dwarfs have a mass limit. If they get above 1.4 solar masses, so 1.4 times the mass of our sun, they can no longer support themselves against gravity, and they too will try to collapse. Except, instead of collapsing to form a neutron star or a black hole, as they collapse, they are going to ignite that material, that carbon or that helium that they are made out of. They're going to they're going to reignite nuclear fusion. And if you reignite nuclear fusion, white dwarf material has this funny property where when it heats up, it doesn't expand too much. And so you don't have any sort of release valve on this nuclear fusion that you just ignited. You just get hotter, and so you fuse faster, and so you get hotter, and so you get fused faster and hotter and faster and hotter and faster until you explode. And so you can think of a type 1a supernova as the universe's largest thermonuclear bomb. So this, unlike a core collapse supernova, which will leave behind that neutron star or in some cases a black hole, a type 1a just blows the whole thing to smithereens. You don't have any white dwarf left, it's gone, you just have an explosion. But the remnants actually look somewhat similar. You know, we colored them differently, but actually that first supernova remnant that I talked about, Cassiopeia A, that was a core collapse. And the second one I talked about, Tycho supernova remnant, was actually a type 1a. But supernovae aren't the only fireworks that I'm interested in. I'll mostly talk about them. They're very near and dear to my heart, but there is a whole wide world of extreme stuff. And if anyone wants to ask me about any of these in the Q&A, I'm happy to do my best to talk about them. But kind of the smallest scale things that I think about are novae, so smaller than supernovae. They just got the nova, they didn't get the super. I really like them though. I will actually talk about them a little bit today. They happen on about the scale of our Earth-Sun system, so it's about 1/1,000,000th of a light year. On the other hand, on the highest scale, so the largest scales, you have galaxy cluster mergers. Galaxy cluster mergers occur when two clusters of galaxies, these are the largest gravitationally bound systems in the universe, crash into one another. They're pulled together due to gravity, they crash into one another, and they will produce shock waves, which you can actually see, if you see that kind of reddish filament in the rightmost image, those are the shock waves due to the collision between two galaxy clusters. And there's all sorts of stuff that goes on in between. Some things are powered by black holes, some things are powered by exploding stars. Stars and black holes can both blow winds. There's all sorts of variety of firework that we can observe. And all of this is a laboratory for extreme physics. These are all parts of the universe where we are pushing the temperature, the energy, the size scale in ways that we could never achieve here on Earth. So we get to kind of take our physical models and crank them up to 11 and see if everything still works. And so the sorts of questions that I'm interested in answering with this laboratory are things like, how do cosmic fireworks evolve? So how do these explosions evolve? How do they die? What was happening before they exploded? Can we predict when the next one will occur? And how do they impact their surroundings? So when you blow up a star in a galaxy, that can be very disruptive. That can change how the galaxy evolves. And so these are some of the questions that we can start to probe by looking at these objects. But I mentioned a lot of different objects, and that's a lot of different science to do. So how are we able to kind of put those all on one plot and say, yeah, this is something we can study in roughly the same way? There is one unifying feature of all of the objects that I showed you. I was very careful to select ones where you could actually see that they produce a shock wave. So what is a shock wave? A shock wave in Tycho supernova remnant is the purple thing. So that purple rim is the shock. But more generally, I'll talk about what they are from a physics standpoint, but I want to emphasize that they are very important physically to any sort of extreme phenomenon like this, any sort of explosion. Because a shock wave is actually what goes through and converts kinetic energy, so the explosion energy, into heat, into light, into magnetic fields, and it is also what can produce those cosmic rays that we've talked about. So those are charged particles, protons and electrons, moving at almost the speed of light that are accelerated by the shock. So in other words, shocks are how cosmic fireworks impact their surroundings. The second thing that I want to say is that shocks are observationally important. So the hot gas and the cosmic rays that you accelerate, those both go on to make light, and that is the light that we observe. So in this case, it's making purple, and actually the hot gas is also making that kind of blobby greenish yellow. That's the hot gas that we're seeing as well. And so that was all heated up by the shock wave. So what is a shock? A shock is a discontinuity, a jump in density, in temperature, and in pressure that you get whenever you have supersonic motion. And you may think, well, there's no sound in space. That's not entirely true. In fact, there is no sound in a vacuum, but there's stuff in space. It's much lower density than you're accustomed to, like 1 proton every cubic centimeter, so not a lot, but there is stuff in space. And that means that you can create pressure waves. Just like the pressure waves that are coming from my mouth as I speak to you, you can also create pressure waves in space. And on Earth, if you move faster than the speed of sound, you make a sonic boom. In space, you make an astrophysical shock. A sonic boom is a form of shock that occurs here on Earth. And it is simply the fact that you are moving faster than those pressure waves, than those sound waves can travel. And so instead, it all gets squished up into a single signal, a single discontinuity or jump in density, temperature, and pressure. And so all of those kind of jumps that you see, this is a special kind of photograph that actually shows how the refraction index of air changes. All of those jumps that you see, those kind of ridges, are shocks being produced as a jet travels through the air faster than the speed of sound. So I'm studying the same thing, just in space. And shocks are cool because they can tell us a lot about the underlying explosion. Again, they're the way that the energy gets transferred. And actually a very classic example, one of the first examples of how a shock was telling us some information about the underlying explosion, took place back in the 1940s when a shock that occurred here on Earth was published in Life magazine. So if any of you have seen this photo before, this was the Trinity nuclear test. So this was the first ever nuclear bomb that was exploded here on Earth. And this picture, after the war, was published on the cover of Life magazine. And they were willing to tell the world, yes, we have nukes, but the US government was not telling anyone anything else about these nukes that we have. This is the beginning of the Cold War. Everything's highly classified. But they messed up because they gave physicists a timestamp and a length scale. So we know how big this thing is, and we know when it was that big. And it turns out, if you do a little bit of physics, you can actually go and say, I know how much energy was released. This is highly classified information. Sir Jeffrey Ingram Taylor published this. There was nothing that could be done about it. He was right. And yeah, that is how information gets declassified, just to apply a little bit of physics. But we can play the same game in space. So I said that Type 1a supernovae are the universe's largest thermonuclear bombs. So we know how old it is, because Tycho recorded it 454 years ago. And we know about how big it is. So the radius is about 12 light years, so it's about 24 light years across. And so we can play the same physics game, and we can say that the energy released was 2 times 10 to the 31 kilotons of TNT. I tried to find a number to put that in some context. The best I could do is that is about 1 million more Trinity nuclear tests than there are stars in the universe. So that's a lot of explosive power. You do not want to be caught in one of these. So shocks can tell us what caused them. They can tell us how energetic the underlying explosion was. They're also particle accelerators. So I've been kind of teasing cosmic rays here and there. These are, again, these energetic charged particles, protons and electrons. Shocks are very efficient particle accelerators. When you think of particle accelerators, you might first think of something like the Large Hadron Collider at CERN. That's what I'm showing here over on the right. That is a man-made particle accelerator. It is an underground ring full of magnets that is straddling the border between Switzerland and France, and uses magnets to send particles, typically protons, around and around, gaining energy every time they go around that loop. Supernova remnants do something similar, although they don't have nice ordered magnets, so they can't send particles around and around and around in neat lines. Instead, what they do is they create a bunch of very messy, turbulent magnetic fields, lots of bumps and wiggles in the road that particles want to travel across. And so as a result, when you have a charged particle in and around a supernova remnant, it's going to wiggle. It's going to take this kind of random, meandering walk back and forth across the shock. And when a particle goes back and forth across the shock, it will start, let's say, first to the right of the shock, like it is right now. And then, when it crosses the shock, it's going to see the flow on the other side moving toward it. And so it's going to get whapped in the face. It's going to have a head-on collision, and that's going to give it some energy. And then it's going to bounce around to the left of the shock for a little bit and kind of get used to the material over there until it meanders its way back across to the right side of the shock, and it gets another hit in the face because it was used to the material on the left side of the shock, and the material on the right comes and hits it with another head-on collision. So you can think of this process, this particle acceleration process, as a sort of frictionless ping pong, where every single time the particle crosses the shock, it gets whapped, it gains energy. And so these accelerated particles are the shrapnel that I'm interested in, and they are the key to understanding some of the light that is coming from this object, because when you accelerate these particles, you get them very close to the speed of light, and then they go on and they interact with stuff. So you accelerate the particles, and then they interact with magnetic fields, with background light, with other protons and electrons. And all of these collisions, these deflections, they are going to produce more light and also neutrinos. Neutrinos, for those of you who aren't familiar, are very light, neutral particles. Because they are neutral, they travel in straight lines. They don't get deflected by magnetic fields, just like the light. However, they are kind of a pain to detect. They don't interact with much. You have tons of neutrinos going through you every moment of every day. They don't interact with you. They don't do anything. We love them. We try to detect them. It's hard, so I'm mostly going to focus on the light. And so the light that comes from these particles is really, again, the shrapnel of the shrapnel. If the particles are shrapnel, it is the shrapnel of the shrapnel that we actually see here on Earth. And so we are really trying to understand all of the physical processes in each of these steps, how the particle gets accelerated, how it interacts to produce light, before we can actually understand what the light is telling us. So when I say light, I also want to clarify that I don't just mean the light that we can see. That is actually only a tiny fraction of the light that you get from a supernova remnant. And so the light that I am interested in spans the entire electromagnetic spectrum. It goes from radio waves all the way up to gamma rays. So if you haven't seen a picture like this before, just know that the wavelength or frequency of light corresponds to its color. We see that tiny fraction, that visible light section. But at the longest wavelengths, lowest frequencies, lowest energies, those are all equivalent statements, you have radio waves. At the shortest wavelengths, highest frequencies, highest energies, you have gamma rays, and then a bunch of stuff in between. So this is many, many orders of magnitude in energy, where you're getting all sorts of different kind of light and all sorts of different kinds of diagnostics as a result. I will also mention, if you've seen any sort of astronomical spectra before, you may have seen this reversed, where you have the purple on the left and the red on the right, because you do it by wavelength, not by frequency or energy. The people who do it by wavelength are what we call wrong. I like to think in terms of energy. So lower energy on the left, lower frequency on the left, higher energy on the right, higher frequency on the right. And so the data product that you actually get from an object like this looks something like this. So what is this plot? This is a spectrum. This is a multi-wavelength spectrum. And so what you're looking at on the y-axis is essentially a measure of brightness. How much light are you getting? And on the x-axis, you're getting frequency or energy. So where in the electromagnetic spectrum are you? And so all of these little data points were taken by a bunch of different telescopes, and then we tried to connect them with these lines. These lines aren't arbitrary. The lines are actually a model. So the lines were us taking all of the physics we think we know about the explosion, all of the physics we think we know about particle acceleration, all of the physics we think we know about how particles go on to produce light, and then asking what should the light look like. And then we tweaked our model, so we changed the parameters of the explosion until we got it to fit the data. And that is actually going to help us answer questions like, how fast is the shock expanding? How dense is the material around it? That can tell us something about what happened before the explosion. How strong is the magnetic field? And the question that is near and dear to my heart, how much energy goes into cosmic rays? So why do we want to know how much energy goes into cosmic rays? How much energy goes into those charged particles that are moving near the speed of light? Well, because there's one more question that I'm trying to answer that has been plaguing astronomers for over 100 years, and that is the question of, where do cosmic rays come from? All of these things that I showed you are capable of accelerating cosmic rays. For all of these objects, we have mechanisms for accelerating cosmic rays. But we still don't know where most of the cosmic rays at any given energy come from. We have some ideas at some energies, but there are huge gaps in our knowledge. So we are trying to narrow it down. And before I kind of go through how we narrow it down or what we're looking for, I want to give some history to this 100-year-old problem, because this has been an issue. We at first didn't even know what cosmic rays were, but it all started, again, back some over 100 years ago in 1912, to be precise, with this guy named Victor Hess. So you can see him here in his balloon surrounded by children. I'm not sure why. But I guess they were very excited to see him go up in his balloon. So what was Victor Hess doing? He was not just joyriding. Victor Hess was very interested in radioactivity and in measuring ionizing radiation. This was an era when we were just starting to learn how radioactivity worked. We had learned that the Earth was a source of ionizing radiation, that certain materials were more radioactive than others. And so he was saying, well, if the Earth is a source of radiation, then as I get further from the Earth, I should measure less of it. So I should get less ionizing radiation as I go up in my balloon. And so he went up in his balloon. Just a fun side note, we still use a lot of balloon experiments in cosmic ray physics, but they are now unmanned unless we have a student that we really don't like. So he went up, and what did he find? Victor Hess found that there was actually more ionizing radiation as he went up, less as he got closer to Earth. And so the question is, why? This means that there has to be some source of ionizing radiation that is outside of our own Earth, some extraterrestrial source of ionizing radiation, and this is what he named cosmic rays. I've been talking a lot about cosmic rays as these energetic charged particles, so why are they called cosmic rays? This guy. They are not rays, we now know that, but we didn't know what they were when we first found them. So they were some sort of cosmic radiation, cosmic rays, not really sure what they are. The name stuck because you name it once in astronomy and that's its name forever. It's like getting a dog. So the debate was on. So this was back when the scientific debates on the cover of the New York Times were very exciting. This was a clash between Millikan and Compton. Those are names that you may have heard before. These were some of the notable names of the day who had very different ideas about what cosmic rays are. Apparently, it got very heated at a conference, which is especially fun when you know that Compton was Millikan's pupil, so got a little spicy. And so you have Millikan saying that cosmic rays are photons, they're light, they are the birth cries of atoms. And then you have Compton who's saying no, they're charged particles. And initially we had no way to resolve this until new data came out that there were more cosmic rays coming from the west than from the east. And so the question is, why are there more coming from the west than from the east? Well, if cosmic rays are charged, in particular if they're mostly positively charged, they're mostly protons, then the Earth's magnetic field is going to deflect those particles in such a way that they preferentially come from the west than the east. And so, because of this understanding of how the Earth's magnetic field would deflect positively charged particles, we were able to confirm that cosmic rays are in fact charged particles and that they are not the birth cries of atoms. If we fast forward 100 years, 100 and more than 100 years, the modern picture of cosmic rays looks like this rather messy plot. So what are we looking at here? This is in fact another spectrum. But instead of showing you the spectrum of light, I am showing you the spectrum of cosmic rays. So the y-axis is the rate or the number of cosmic rays that are hitting the Earth, and the x-axis is the energy of those cosmic rays. So this is basically taking all of the cosmic rays and categorizing them by the energy that they have. So in a plot like this, the oh my god particle is going to be that data point on the very, very far right. The oh my god particle, by the way, has about the energy of a pitched baseball in 1 proton, which is a lot to put in 1 proton. So this is what we see today, and we can see if you look at that kind of top component, the data that's kind of the highest level, those are all protons. So we know they are mostly protons. There are electrons in there, there are some other particles in the mix, but again, it's mostly protons with some contribution from other charged particles. But then we get back to that question that I introduced before, which is, where do these things come from? And so we do think that at the lower energies, supernova remnants are the answer. We know that these cosmic rays are galactic in origin, and we know that supernova remnants provide enough energy to give us all of the cosmic rays that we see. So if you take all of the supernovae that go off in our galaxy, convert 10% of their energy into cosmic rays, you can fully reproduce that spectrum. So that's very promising evidence for the cosmic rays coming from supernova remnants. Great, we solved a little bit of it. The problem is when you get to higher energies, starting with, you can see that place that's labeled the knee. So we describe the spectrum as a leg, so there's a knee and there's an ankle because of all the features. So the knee is where things get tricky. It doesn't seem like supernova remnants can accelerate particles quite that high in energy. They seem to crap out on us, which is too bad. So we need something else at the knee, and then we definitely need something else at the highest energies where we know that they are extragalactic in origin. This is where the jets that we saw in the trivia session seem very promising. We don't know that they're the source of cosmic rays, but they're a very energetic thing, and there are a lot of ways to accelerate particles in a very energetic thing. So that seems like a promising place to look. But this does beg the question, it's been 100 years. Why is this so hard? Why can't we just look up at the sky and be like, that's where the cosmic rays are coming from? Come on, guys. And so the reason that this is so hard, the reason this has been so difficult, is related to the same reason that magnetic fields accelerate charged particles. Magnetic fields deflect charged particles. And there are a bunch of magnetic fields between us and the sources of cosmic rays. The galaxy is full of them. And so that means that the cosmic ray that you accelerate, say at Tycho supernova remnant, takes this kind of meandering path from its origin to the Earth. And so we have no way of knowing where it came from because it was bounced all over the galaxy before it got here. And that is why we like to look not at the charged particles themselves. They can tell us some information, but they can't tell us where they're coming from. Instead, we look at the light and the neutrinos that they produce in their sources, the byproducts, the shrapnel of shrapnel. Because light and neutrinos are not charged. They travel in straight lines. And so that makes our life a whole lot easier. And so the hunt is on. This is a very small sampling of some of the instruments that are looking for evidence of particle acceleration. If I have missed your favorite instrument, I'm sorry. There are lots of other instruments doing this science as well. I just wanted to kind of give a sampling of the different energies we're interested in. So we have radio telescopes. Meerkat is the shiny new radio telescope that's coming online. We have NuSTAR, which is a very high energy X-ray telescope. Fermi is near and dear to my heart. Fermi looks at what we call GeV gamma rays. So we measure the energy of both gamma rays and charged particles in electron volts, or EVs. And so a GeV is a giga electron volt, so a billion electron volts, like gigabyte. And so Fermi is very near and dear to my heart because this is a particular range of energy where I think we can do a lot of diagnostics. We can learn a lot about the spectrum of a supernova remnant, or from the spectrum of a supernova remnant. But Fermi is the only thing in the sky that is looking at those energies. And it was launched in 2008. And so we all just need to keep our fingers crossed that it stays up there and stays working. So. But there are some really exciting new higher energy telescopes coming online. The Cherenkov Telescope Array is kind of the next generation. It should be up and running in the next few years. That's looking at TeV, or tera electron volt gamma rays, so trillion electron volts. LASO, which is looking at peta electron volt gamma rays. This is a telescope located in China. And then lastly, we have a number of neutrino detectors. The current state of the art is IceCube. It's located at the South Pole, but there are new detectors coming online for this field as well. So just to kind of give you a sampling, these are all of the places where we can look. One of the other places that I've been really interested in, and I just want to finish with this object. This is not going to be the source of our cosmic rays, but it is very near and dear to my heart. It is one of my favorites because I think they punch above their weight, and these are objects called novae. So these are the smallest thing I showed you when I was showing you all the different fireworks. They're just the size of our Earth-Sun system. You think, why do I care about these dinky little explosions? Well, these dinky little explosions are very useful because they are good test beds. They happen frequently and they evolve quickly. So all of our models for, how we think shock should accelerate particles and how the particles should produce light, we can test all of that because we have kind of repeated instances of these explosions. So what is a nova? A nova is kind of like a mini type 1a supernova. So it is where you have a white dwarf, that's the white blob there, but its companion is not another white dwarf. It's in a binary, it has a companion, but the binary companion is a still living star. So a star that's still fusing, it's much puffier, and because it's much puffier, it's going to be lower density, and it's going to lose material to the white dwarf. Whenever you have a binary system, the denser body wins, the denser body pulls material from the companion. And so the white dwarf is going to be eating material. And I mentioned before that white dwarf material is funky. White dwarf material likes to ignite runaway fusion because it doesn't have much of a release valve. If you get it hot, it just keeps getting hotter. And so what that means is if you accrete a little too much material in just the wrong way, you can ignite runaway nuclear fusion. And so you have a little, but still pretty big, thermonuclear bomb. And so a nova is just that. It is an explosion that is coming from a white dwarf, but it is not catastrophic. It doesn't completely destroy the white dwarf. And so that means these things can actually be recurrent. You can have a little explosion and then go back to stable accretion and then go off again. Some of these go off every 20 years. And so again, I like these objects because not only are they recurrent, but they're frequent. So with gamma rays, we detect about one of these every year in our galaxy. The overall rate of novae that we detect with other telescopes is much, much higher, but I'm kind of filtering to the gamma ray ones because the gamma ray ones are the most powerful, the most interesting to me. And the second thing is, again, they evolve quickly. They're fast, but not too fast. And what do I mean by that? Well, they last for about a month, which is nice because a supernova remnant takes somewhere between 1,000 and 100,000 years to evolve, depending on how you look at it. And I don't know about you, but I don't have that kind of patience. A nova will go through all of those same stages, but over the course of a month, and I can wait for a month. I can handle that. But also, they're not so fast that it's impossible to point your telescopes in time. You have some time to get your telescopes aligned and to actually look at this thing. So it's a nice Goldilocks, it's a nice test bed. And an example of one that I spent a lot of time looking at was this one called Arasofukui. So Arasofukui went off in 2021. On the left there, you actually see this was an image captured by amateur astronomers. One of the main ways that we detect these things is amateur astronomers find them and tell us that this happened, and then we go and point our professional telescopes. And then on the right, you have, again, a spectrum. This is a spectrum at 2 different times. So the green was first, and then 5 days later, we got the purple. So again, this is brightness versus energy of the light. And we actually detected TeV, tera electron volt gamma rays. This is exciting because we've never detected TeV gamma rays from a nova before. We didn't think they really would be capable of producing TeV gamma rays. This thing is accelerating to like the absolute maximum energy we think it should be able to accelerate. So this thing is kind of punching above its weight, and it might tell us something about how particle acceleration occurs in larger systems. The other thing is when we tried to go and actually fit a model to fit those solid lines through it, we couldn't do it with that spherical picture I showed you before. We couldn't make that picture on the left work. And so what we actually settled on was we were seeing evidence for a picture that's closer to the one on the right, where instead of having just a nice, neat spherical explosion, you have these 2 lobes that are coming up, and then some kind of denser, funky region in the middle, likely due to the binary, likely where the 2 stars are orbiting one another. And so we were able to kind of change the picture, and this may be relevant for supernovae as well, because a lot of supernovae, not just type 1As, but actually core collapse supernovae, go off in binary systems. And so I want to finally leave you with something to get excited about for the future. I wanted to bring up novae in particular because there is a very big nova that is supposed to go off any day now, and by any day now, it was supposed to go off this summer, but it didn't. So this is T Corona Borealis. It may be our next cosmic firework. It is both closer than Arasofukui and is expected to be more powerful. It goes off about once every 80 years. Again, we were due to go off this summer. It's not an exact science, more like predicting the weather. But keep an eye out for this next cosmic firework. It will be very exciting, and when it does go off, it will be visible with the naked eye. So that brings me to the end of my talk. Thank you so much for your time. And if you have any questions, feel free to email me as well.
All right, thank you so much for that fantastic talk. If you'll advance the slide. All right, so there are 2 ways you can ask questions. You're welcome to raise your hand. We'll only do a few questions, so I apologize if I don't call on you. But if you'd rather write down your question, you can scan the QR code or go to this link, and your questions will show up on my computer. So we'll go ahead and start with questions. Let's see, Angie.
Yeah.
All right, so looking at this, where you have all of these different mechanisms, how small are microquasars?
So they are micro relative to what we call regular quasars. So a regular quasar is actually a subcategory of active galactic nuclei, so the next one up on there. So a regular quasar occurs when you have a supermassive black hole at the center of a galaxy. It's eating material, and then it can launch these big jets. It can produce a wind that propagates through the galaxy. A microquasar is the same phenomenon, but instead of using a supermassive black hole at the center of a galaxy, you have a regular stellar mass black hole, so like what's left behind after some core collapse supernovae. So you have a regular stellar mass black hole. It's got a binary companion, and it's eating its binary companion, still launches jets, still makes winds, but it is micro because it is technically like a millionth the size of a macro quasar.
All right, question right in the front row. Yes.
For novae, why doesn't why don't novae block their entire length?
Yeah, why don't novae blow up the entire white dwarf?
Yeah, so that's actually a tricky problem. And people have been wondering for a long time whether you could eventually get to the point where you do blow up the entire white dwarf. But the thought is that when you are eating material, the hottest spot is just on the surface. And so the part that gets ignited is just on the surface. It blows off very quickly because it gets so hot so quickly. And then the rest of the white dwarf is left behind pretty much intact. When you explode in a type 1a, you're usually merging two white dwarfs, at least we think that's the picture. But either way, you are igniting the core of that thing. So you're igniting it from the inside out, and so everything blows up, not just the surface.
Okay, question. Yes. So the cosmic expansion of the universe, has that affected the number of cosmic rays we've observed?
Yeah, cosmic rays or cosmic fireworks?
Fireworks, thank you.
Yeah. So not too much. We do have to account for it for the most distant fireworks. So the ones that are, at galaxies that are very far away. But most of these surveys that we're conducting are pretty local. We can't actually go that deep. That's going to change with next generation instruments. But because we can't necessarily see these fireworks when they're happening too far away, we're not as sensitive to the expansion of the universe.
Okay, question here. Will you go back to the question QR slide?
When was the first supernova discovered?
When was the first supernova discovered?
Yeah. So that was the one that I talked about at the very beginning. So that was in the year 184, I want to say. The 180s. So it was almost 2,000 years ago.
All right, a question online. So if you're looking at the shrapnel of shrapnel, how can you be sure that the first set of shrapnel is being created?
Yeah. So there are a few telltale signs. It depends a lot on what kind of light you're looking at. The kind of very good hint, and one of the reasons I really like gamma rays, is there isn't really anything else that can make light with that much energy. You need to have a really energetic particle first. So kind of by process of elimination, you can't just take light, because light is neutrally charged. It has no charge, which means you can't bump it around with magnetic fields. You can't really do much to make it into a gamma ray unless you produce it using a parent particle that is a lot more energetic. So we know that you need to, in order to make gamma rays, you needed to start with something that had about 10 times more energy than the gamma ray you produced. And so that's how you need to have that first round of shrapnel. You need to have those cosmic rays.
All right. Yep. Good. So for this note, 150 days, or should we be looking in the sky?
Yeah, well, that Forbes article was published in January, so the 150 days is definitely wrong. As far as where, I should know this, and I don't, and I will get back to you. Yeah, I don't know my constellations as well as I should.
And that is another difference between professional astronomers and amateur astronomers. One can tell you what you're looking at, the other cannot tell you what you're looking at. Okay, we'll do one final question here.
I'm just curious about planetary exploration. Will going to Mars make a difference in analyzing?
Yeah, so if we tried to look at this kind of data from another planet like Mars, will that help or affect?
So Mars won't change too much because while it's true that Mars does not have a magnetic field, and so it's much less insulated from cosmic rays, that's a problem for astronauts, we have space telescopes that can go and measure cosmic rays, and so we can get out of our own atmosphere as well. So that's less of an issue. The place you want to go if you want to kind of have a fresh take on cosmic rays is actually outside of our solar system. So the Voyager 1 spacecraft has actually made it past the solar wind. So basically past the influence of our sun, which can actually affect the lower energy cosmic rays. So Voyager 1 is actually taking data on kind of pure, fresh cosmic rays that haven't been modulated or affected by the sun.
Okay, we're gonna end questions for now. Let's give another round of applause to Rebecca. If you have a question, she'll stick around for a little bit after the talk. We'll do our raffle now. So how this works is look at the number on your seats. Usually these are used to assign seats during scary exams, but we use them for fun. I have a random number generator. If I say your letter and number, please shout really fast because I only have 4 prizes, so don't let me overpromise. Okay, E5. Woo, all right. P12. A9. Okay. I said P12? P12, all right. Where am I? G16. C1. E9. Yes. And then E. Yep. Okay. B1. N1. All right. So in a moment, you can come down and get your prize. But I have our weather report. Drum roll, please. We are going to be observing. Yay! All right. I have some instructions, so please listen carefully. I'm going to skip by this side. There are 2 possibilities for observing. You can do both, but only one is accessible, unfortunately. Our roof is a historic dome. As I said earlier, it's turning 100 this year. So you need to go up 2 flights of stairs to get to this telescope. If that's something that sounds fine to you, our dome is an option. I will also have a telescope right outside of this building that requires no stairs to go up. So you're welcome to go to either of those or just the one that is best for you. So I'll be right in front of Pupin. For the roof, not yet. Okay. For our roof, we have our 2 volunteers here, Viraj and Afam, who have been setting up the telescope. They're going to lead folks up to the roof. It seems like we are down an elevator today, so we're just going to take turns. Only about 15 or 20, 25 people fit in the dome at once, so there's going to be a little bit of a line in the stairwell. Everyone is going to observe, so don't worry if you are in the line. Let's see, what else? Oh, it is on the roof. The roof is full of trip hazards, so please do not wander around the roof. We will not be able to use the roof if someone gets hurt on the roof. All right, if there are no questions about that, we're going to have our volunteers help bring you up. Thank you so much. Have fun. All right, enjoy. Thank you all for coming. If you want a prize, come see me on your way out. Great question, by the way. Yes.